Assalamu alaikum. Good evening, everyone. My name is Ahmad Mustafa, and I'll be your host for today's webinar. It's my pleasure to introduce our speaker, Engineer Muhammad Mustafa, Senior Production Technology Engineer with over 13 years of experience in the oil gas industry. He started his career in the field with well intervention, workover, and stimulation operations, and later joined the WRFM team for well restoration and optimization. Currently, he leads the artificial lift team, handling ESP, SRP, and PCP systems from design to troubleshooting. We're glad to have him with us today. Welcome, Engineer Muhammad. And just a quick note before we begin, I'll be sharing the link for the webinar certificate from form in the Zoom chat. So please make sure to fill it out. Engineer Muhammad, the mic is yours.
Okay, thank you, Engineer Ahmed, for your kind words and welcome for all. Good evening for all, and we hope this webinar to be useful for you all. I also will start sharing presentation now. So please confirm if you are all can see my presentation. If it is okay, I will start now. So our webinar today will be as a summary and or introduction for the main course that will be around the nodal analysis in oil and gas wells, how to understand the nodal analysis, how to differentiate between the IPR and VLB, and how to understand the full system interpretation. Also, it will be have some basics for the artificial lift design and equipment. In the main course, we will go in deep details for the equipment, the breakdown for the equipment in different artificial lift types like sucker rod, ESP, PCB, jet pump, and so on. And we will give also a hint around the design. We will give some example using softwares like PipeSim and Prosper for the design of the artificial lift and for the nodal design. So we will give today, inshallah, just a summary for our course. But before to starting our nodal analysis interpretation or summary, we will have to give some information or refreshment about the oil field life cycle. As we all know, we have three main stages for any oil or gas field. The first stage is the exploration stage or the first phase of exploration. In this stage, any company that own the rights for exploring or developing defined concession in any country start by seismic survey. This seismic survey start to searching about a trap or a reservoir that may contain a hydrocarbon. This is done by some geophones and some receivers using trucks. They perform some interpretation for this data, and geophysicists and petrophysicists start to analyzing this data, searching for traps, because we all know that hydrocarbon are found underground inside a trap. Once they found this trap and they say that it is possible to contain a hydrocarbon, they start to drilling the first well in the concession, which is the exploration well, and sometimes it's called a wildcat well. Then, based on the test for this first well to be drilled, it can be drilled more and more wells for more testing and more exploration. So this is the first stage of any oil or gas field. Then, once we confirm there is a presence of hydrocarbon, even oil or gas, we start to develop this concession or develop this field, which is the second stage of any field by drilling more wells nearby the first wells and they develop production from this concession. By drilling more wells and more wells, we start to evaluate this reservoir, estimate the volume, perform testing, build up test, and reservoir limit test to see how much volume we have inside this field, and we decide the field development plan or how much wells we will drill and we will produce. After drilling the wells and complete it with tubing and bucker or even artificial lift, if the reservoir is not capable to flow naturally, we start to building the pipelines and the production facilities to receive oil and gas from these wells and start shipping to the manufacturer. This is the middle stage. So the first stage is exploration. The middle stage is development and production. And wells and reservoirs, or even the total field is continue production. It can reach 30, 30 or 40 years of production until we reach the final stage of any oil and gas field, which is plug and abandonment. Once water cut increased or become not economic to operate this field, and no oil is produced with the economic limit, we start to plug the wells and abandonment these wells and keep the location of the wells to restore it to its original phase. So three main stages: exploration phase, the development and production phase, then the plug and abandonment phase. This is on the level of the total field. But let's concentrate more deep on the well and reservoir level. We can found that oil pass during production. How can we receive the oil from the underground? First of we all know that the hydrocarbon is present underground inside a reservoir. This reservoir is a trap that contains the hydrocarbon inside it. It may be oil or gas. There is many types of reservoirs or the drive mechanism that we all know. We may have hydrocarbon in the middle due to gravity, and under the hydrocarbon we can find water, and above the hydrocarbon we can have the free gas or the gas cap. This is the reservoir. We have hydrocarbon trapped underground, and it can't move away from this reservoir or from this trap because we have a cap rock here or seal element that preventing the escaping of the hydrocarbon. We all know that there is different mechanism of reservoir. We can have a hydrocarbon only, which is a depletion drive mechanism. We can have hydrocarbon and water below it, which is called strong aquifer or even aquifer drive mechanism. We can have only the gas cap, which drive give energy for the hydrocarbon to reach surface. We can have a combined drive mechanism that we have in this picture. So first of all, the hydrocarbon is present underground inside a reservoir, contained inside a reservoir. So how can we get this hydrocarbon, even oil and gas, to be moved from the downhole to surface? We start to drilling a well. We drill a hole, then complete this hole with casing, tubing, and bucker, perforate inside the hydrocarbon zone or the interest zone that is contained hydrocarbon, then start to complete the well with tubing and bucker. Then the hydrocarbon will flow from the wellbore to the surface, as we can see here in the second picture, which is the flow of the hydrocarbon from the downhole until it reach surface. Then after it reach surface, it will move through the pipelines to the production facilities. Then it will be shipped to
Hello.
the factories. If there is any problem in the sound, can send me in the chat.
Hello. السلايد مش بيتحرك. السلايد.
So I didn't mobilize to the next slide. Still on the second.
I think previous structure. It's showing only slide number 1.
Still here.
The screen is showing about the screen number slide number 1. Yeah, now it's changing.
So now we in the slide number 3. Is it clear? We
Yes,
are now
Henry.
on, yes,
Yeah.
on the slide number 3. So we were speaking about the oil pass during production. It's moving from the reservoir through tubing and through the wellbore. Then it would move to the surface to the flow line and to the separator. So moving to next slide. I hope the next slide changed. So as we can see here, we have two different types of location. We have wells that may be drilled on land, which is called onshore, and another which is offshore. It for sure the cost.
Slide number
Sir, we are still on slide number 3. Okay.
So give me a second here. Okay, so it's appear now that we have two different locations for the wells. We have wells that's on land, on onshore, and another which is onshore. For sure, if we compare between the two, we can find that the offshore cost a lot of money because we have to bring drill ship or jackup or semi-submersible to start drilling. So this is the classification
Hello,
of wells based on well location.
sir. Excuse me, sir.
Go ahead.
Sir, can you show the slides in slideshow, sir? Because the screen view will be very clear,
Okay. I shared now.
sir. Because
The
if you turn on
slideshow.
the slideshow, it will
Yeah.
be automatically switching to another slides. Press F5, sir, for slideshow.
Okay. So I moved now to next slide about the well types. Is it changed at yours?
click F5 to enter slideshow mode.
I already did. So let me stop share and share again.
Yeah, can you share again?
So I think it is appeared now.
هذا
Can you share the second slide?
It is already
Sir,
on the slideshow now.
just click the F5 button, sir. F5 button. Then you can able to show the slideshow.
I already put it on the slideshow. So can you tell me which slide you can see now?
Well types.
Well
Well type.
types, sir. Well
Yes.
types.
Yes. Yes. So for the well types, we have different types of wells. We can have oil well, that is natural flow or artificial lift. In these types of wells, we can produce only oil from this well. If we are deciding to drill an oil well, we have to consider because we have to selecting some casing and the tubing material that can sustain with oil. The same we can have a gas well, which we will need to have another material that's suitable for gas. For example, you have to utilize a premium connection to avoid leaking between the joint. And we can have a water injector well. This well is used to inject water from surface to downhole to support the reservoir or to increase the reservoir pressure to compensate the drop in reservoir pressure due to production. Another well type is water source, in which well is completed with ESP or a pump that will provide the water to the water injector well. So, is voice is still clear? So you still with me or something in the voice?
Clear.
Okay. So the last well type is observation well, in which we can drill a well and record the pressure to measure the reservoir pressure or to monitoring the oil water contact with, which is moving while production to detect when which zone will be perforated later in the well that will be drilled. So as a summary for the well types, we have oil well, gas well, water injector well, water source well, water disposal well, and observation well. So moving to the next slide, we can have a well life cycle. So we now will discuss the life cycle for a well itself. We discuss the life cycle for the reservoir, which is starting from the exploration phase, passing by the production and the development phase, ending with the plug and abandoned phase. But now we will discuss the life cycle for the well itself. Any well, even water or oil or gas, starting with the planning and design stage. After completing the exploration phase, deciding which location will be started for the drilling, and the reservoir team has completed the assignment for the target zone, and well design is completed, material was selected. We will start with the drilling, which is the second phase for the well life cycle. So the first phase is planning and design, then the execution phase by bringing the drilling rig to well location, start drilling the well and perform the casing and cementing for the well. Then moving to the next stage, which is completing or completion. It can be done by a drilling rig or it can be done using a workover rig, depending on the policy of the company. During the compression phase, we perform the compression by bucker and tubing if it is producing naturally or by artificial lift. Then start testing the well. Testing can be for short period for a few hours or can be a few days depending on the policy. Then the workover is or the drilling rig is released and well is diverted to the production, which is step number 4. We start production from the well and perform optimization and monitoring for the production rate and for the artificial lift, and perform optimization and monitoring if we want to increase the rate or decrease the rate to control the drawdown from the reservoir. Then the following stage is maintenance and workover, because as we all know, during the life cycle of the well, any well may need some routine work for maintenance, some workover operation, because if it is, for example, completed with artificial lift type like SB or sucker rod, it may fail after a few months or few years and they need a replacement. So I have to work over the well to restore production. Then after well came to end and water cut increased to 100% or will become dead and can't produce even with artificial lift, we reach to the plugging or the abandonment stage. Then after the abandonment, we retrieve the tubing, perform cementing for the well, and perform some monitoring to confirm that there is no leakage or no or something that reach surface after the securing. So the life cycle for any well start from planning and design, drilling, completion, production, maintenance and workover, plugging, and end up with decommissioning and post abandonment monitoring. So moving now to the next slide, which is completion type. We have two main completion types. We can complete the well using open hole or cased hole. In open hole, the casing doesn't reach the bay zone or the production zone. I produce the fluid from the open hole zone. But in cased hole, I run the casing to pass totally till the end of the well, and the production zone will have a casing against it and cement. Then, before running the completion, I perforate this casing and cement to allow the fluid to flow from the formation to the well. So both types are existing, and there is some advantage for the cased hole over the open hole completion. If we see the next slide, we can have the advantage of cased hole completion. It allows selective production for each zone. If I have a multi-zone of interest, I have two oil zone or two gas zone, and I need to start from production from the bottom zone first, then go up to the upper zone. In this case, I can't do this while using an open hole completion. But in case hole, I can put a bucker between the two zones, produce first from the lower zone, then after that I can go to the upper zone even by workover or by using SSD and a wireline plug. As we can see here, it allows us for isolation for the gas or water zone by bridge plug and producing from the upper zone. Also for the stimulation or a frac, the cased hole completion can give me the privilege of using a hydraulic frac because open hole I can't frac all the open hole in one time. It also allows sand control. I can put some sand screen or something that prevents the sand from going inside my well. Moving to the next slide, which is well trajectory. As we all know, we have a well that can be vertical. In this case, the measured depth is the same like the true vertical depth. I have a deviated or slanted well, as we can see here, in which the measured depth is much more than the TVD because we have a slanted or have we angle here. And we have also horizontal well. We have vertical section here. Then we have a horizontal section inside the reservoir or inside the interest zone. The advantage of the horizontal well that the connection between the well and the reservoir is much longer than the deviated and much longer than the vertical well. Because if we can see here, the part of well that is penetrating the reservoir is much longer than in deviated and in vertical well, which allow more production from this well. But for sure, it will cost more and more money than the vertical and slanted ones. Moving next to the types of wells, we have two types. We have self-flow oil well and the non-self-flow. We move to the slideshow. In self-flow oil well, this well have the capability to bring the oil from the reservoir to the surface because the reservoir itself have a high pressure. This high pressure can overcome the friction inside the tubing and can overcome the hydrostatic pressure inside the well and the wellhead pressure and can bring the hydrocarbon from the reservoir till surface. Also, if it is have a high gas oil ratio can also help to bring the hydrocarbon from the reservoir till surface. Another type is non-self flow, in which we have a dead well or depleted reservoir that doesn't have the energy to bring the fluid from the reservoir to surface. So the main types of oil wells is self-flow oil well and non-self-flow oil well. So moving now to the next slide, which is system performance. This is the first slide that showing the nodal analysis, because what is nodal analysis? Nodal analysis that showing the relation or describe the relation between the pressure and the flow rate inside any part of the well. It is in the downhole against the perforation or against the formation or inside the tubing until reach the surface. The nodal analysis is describing by a system performance that showing me if the well is capable to flow naturally or it is not capable to flow and need artificial lift. The main two components of system performance is the VLP and IBR. The VLP is vertical lift performance, which is mainly represents the fluid flow through the well itself, through the tubing from the bottom hole to the surface. The another concept is IBR, which is inflow performance, which is mainly describes the fluid flow inside the reservoir itself. So we have two main component in the system performance. We have VLP, which is vertical lift performance, and we have IBR, which is inflow performance. Moving now to the next slide. That will we discuss the VLB. Imagine that we have Imagine that we have a reservoir here and we have two wells drilled in the reservoir. One is vertical and one is deviated. So the flow will moving from the reservoir here through the formation to reach the bottom hole, then flow to surface through the well. Okay, moving to the next slide. As we can see here, what is describing the fluid flow through the porous media or through the reservoir? It is Darcy law or Darcy equation. Darcy equation is describing the fluid that is moving inside a porous media. As we can see here, we have a porous media. We have 2 points, point A and point B. Point A is high pressure, point B is low pressure, and we have L, which is representing the distance, and we have A, which is a cross section of this porous media. As we have a high pressure in node A and low pressure in node B, the flow will move from node A to node B due to the differential pressure. So it can be described by this equation: Q equal K multiplied by A by delta B divided by the mu, which is the viscosity, and delta L, which is the distance that the fluid will move. So here we can found that the flow is directly dependent on the pressure exerted on the fluid. And the fluid will move from the high pressure to low pressure. How can we apply this? How can we apply this on our reservoir? We can see here in the next slide. It can be described by a radial flow because we have well is drilled inside the formation, as we can see here in the small circle, and we have the reservoir boundary by this big circle. This is a cross section inside the reservoir. We can have the RW, which is the radius of the well, and we have the RE, the radius of the reservoir. So in this case, how can the oil move through the reservoir? It will move from here, from the boundary of the reservoir to the downhole or to the well. It can be described by this equation, and they included in this equation the K, which is the permeability of the reservoir, the H, which is the thickness of the interest zone or the thickness of the formation, and multiplied by the differential pressure between the reservoir and between the well, because we have high pressure here at the boundary of the reservoir and low pressure at the bottom of the well. So the fluid will move from the reservoir to the well bore. So divided by the mu, which is the viscosity of the well, multiplied by ln RE divided by RW. So this is the application of Darcy law that describing the fluid movement or the fluid path inside the reservoir itself. It can be described by Darcy law. Moving to the next slide, that showing the movement of the fluid also from the reservoir to the well. As the flow is flowing from the boundary of the reservoir to the bottom of the well, there will be a decline in the pressure. Why decline in the pressure? Because There is a friction inside the reservoir itself. There is a resistance for the fluid to move inside the reservoir itself. So we have a decline in the reservoir. For example, we have reservoir pressure 3000 psi, and we have bottom hole flowing pressure here like 2000 psi. So the difference is 1000. 1000 is equivalent to the resistance of the reservoir to for the fluid to moving inside the reservoir. This is for the inflow performance. We can see here the known equation for Darcy, but we replace the K and H and cross section and so on by a constant cooling productivity index or PI. It is described by this equation. The Q or the flow rate equal a constant which is productivity index multiplied by the drawdown. The drawdown is the difference between the reservoir pressure and bottom hole flowing pressure. Next slide here showing the well-known chart of the inflow performance, which is describing the reservoir. We can have here, let's concentrate first for the straight line, which is in red light. We can have here relation between the bottom hole pressure or the pressure on y-axis and the flow rate on x-axis. Assume we have zero flow rate, so the pressure will be the bottom hole flowing will be equal to the shut-in or to the reservoir pressure or the static pressure. And here the intersection with x-axis, it is the maximum flow rate that can be bring from the well. This is a theoretical point because in this case we have to make the bottom hole flowing pressure is zero. In this case, you will have the maximum flow from this well. The straight line can be drawn only in the case of single phase. Single phase, it means no gas presence inside the reservoir, or it means that the pressure is above the bubble point. So the IPR will be a straight line. But what will be the case if we have the reservoir is undersaturated or the below the bubble point? So below the bubble point means that there will be a free gas or a gas in the system. So there is another equation will be expressing the inflow performance, which is Vogel IBR. Here is the equation that describes the IBR but in multi-phase, which in the case that reservoir pressure is below the bubble point. And when we want to draw it, it will be this curved line. This curved line, it will describe the IBR in multi-phase. So moving to the next slide, which is the difference between the two. The constant BI method, it will be in the reservoir that the pressure is above the bubble point, so no gas in the system, and the production is above the bubble point. In some cases, it can be high water cut, but it's not all in all cases. But the another way, which is Vogel, it will be in a gassy fluid on the producing below the bubble point. So there it was the concept of the IBR, which is inflow performance or the equation that describes the fluid flow through the reservoir itself. But now we will move to the vertical lift performance or the fluid flow through the well itself. As we all know, we have a well drilled in the reservoir. This will have a lower pressure than the reservoir pressure. So the flow will move from the reservoir to the bottom hole. Then it will move from the bottom hole from the well to the surface. If we go back to this slide here, we see that the flow will move from the reservoir to the bottom hole here from the well, which is described by the IBR or inflow performance. But once the flow of the fluid is flowing from the bottom hole of the well to the surface, it will be described by VLP or vertical lift performance. The higher pressure we have here, it will be more capable enough to bring more fluids to surface. So I need more pressure here to make the fluid is able to reaching surface. So I have to be optimized between the IPR and VLB. I need to have low pressure in the downhole sufficient to bring fluid from the reservoir, and in the same time it should be high enough to make the fluid to move from the downhole of the well to the surface. So back again to this slide in this chart, we can have that the VLB is a relation between the pressure also and between the flow rate. We have two areas. We have the unsteady flow and the steady flow. We will be concerned with the steady flow because in this case it will be high pressure, high rate, sorry. The flow is high and the dominant factor is the friction because the fluid need to be have more energy to overcome the friction inside the tubing and reach the surface. But this small portion in the dominant here, it is once you are about to start or to open the well. So the dominant here is the hydrostatic pressure. Once you open the well, the rate will increase because there is a decrease in the hydrostatic pressure. But we will concentrate only on the steady flow here. There is many factors that will affect the VLB or the outflow, like the wellhead pressure. The higher wellhead pressure can make the well flow with lower rate. The depth also is controlling the VLB due to the high hydrostatic pressure. Also, water cut, gas oil ratio, and oil density, the geometry, flow regime if it's single phase or multi phase, and the flow rate, tubing size also is controlling the VLB. So now we understand the difference between the VLB or the outflow performance or fluid flow inside the well itself and the IBR or inflow performance, which describing the flow inside the well, inside the reservoir itself. So now we have two figures. We have the IPR and we have the VLB. What will be the case if we draw the two figures on one figure? That's what we see here in next slide. We can find this intersection between the two curves, which means this will have the energy to flow naturally. We have the IBR here, we have here the reservoir pressure, here is the maximum flow rate or absolute open flow. This is the VLB. There is an intersection between the two curves, which means the well is have the energy to flow to surface. So what will be the case? Here, if the energy drop or the reservoir pressure drop with time, as we can see here, the reservoir pressure here will be decreased from the initial pressure to be here to a lower value. In this case, there will be no intersection between the VLB and the IBR. In this case, well will stop flowing naturally and need assistance or need to add more energy to the system to allow the well to flow. This happens during production naturally because with time you will lose more energy from the reservoir or from your system, or even due to back pressure or increase in water cut. So you will need to give more energy to your fluid to reach the surface. So this is the advantage of nodal analysis because it can give you an image or can you give an impression when will produce naturally and when it will stop producing naturally and need artificial lift. So moving to the next slide, as we can see here, it is the impact of the tubing size or the wellhead tubing head pressure. As we can see, if the tubing head pressure is lowering or decreasing, we have tubing head pressure 1, tubing head pressure 2, tubing head pressure 1 is more than tubing head pressure 2. So in tubing head pressure 2, you will have here, you have more production because you have less back pressure against the well. So decreasing the wellhead pressure from 1 to 2 will give you an increment increase in the production rate. So this figure here showing us the effect of decreasing the wellhead pressure. Also another figure here that showing the different tubing size and the effect on VLB. We have the IBR here in blue line. We have the VLB with different tubing size. We have 278, 4 inch, 5 inch. So increasing the size of the tubing will give you more rate because you will have less friction during the fluid moving from the bottom hole to the surface. The same in next slide here for the bean size or a choke size. So increasing the choke size meaning increasing in or decreasing in the wellhead pressure meaning more rate. As we can see here, the rate in case of 32/64 choke is much higher than the first choke. Another concept also here is the gas liquid ratio. Increasing the gas liquid ratio via production will increase the rate because more gas liquid ratio meaning more gas in the system, meaning the fluid is lighter and it will move easily to surface. Moving to the next slide here, as we can see, we have a drop in reservoir pressure from this line to this line. So how can I bring well back to production without changing the VLB? I can do this by increasing the reservoir pressure itself. How can I increase the reservoir pressure? By injecting water or injecting gas. As we said in the first slide, there I have many types of well. I can have oil producer or water injector. If I utilize a water injector well, it can inject water inside the reservoir, increase the reservoir pressure, and bring well back to production. Here will cease to flow naturally. Once I support the well by water injector well, I have the intersection again and well back to production. Next slide here, if I have a well that is not flowing naturally or not producing, I can enhance the well productivity or the productivity index by doing some stimulation for my well. Stimulation can be reperforation, acidizing, fracking, or some treatment using some chemicals. It will increase the slope of this line and make the IPR intersecting with the VLB, and in this case, well will flow. Another also concept which is concerned with our course, it is the gas, the artificial lift. In this case, I will not change the IBR itself, but I will change the VLB. I make it this curve will be lower by adding more energy to the fluid. I can use gas lift, ESP, sucker rod, or jet pump. For ESP, sucker rod, jet pump, or any pumping, I add energy to the fluid so it can overcome the hydrostatic and the friction and reach surface. But in case of gas lift, I don't add energy. I just making the fluid lighter by injecting gas in the down hole. We can understand this by using this curve. I have this a shut-in well. We have a reservoir pressure, and if we do the gradient, I can found it is reached the shut-in tubing head pressure. Once I open well for production, there will be a drawdown because the pressure at the bottom of the well will be less and allow the flow from the reservoir to the well bore, and this is the gradient until it reaches surface with a wellhead pressure. But what will be the case if the well is dead? This is in the next slide. As we can see here, the reservoir pressure, if we draw the gradient, so the fluid level can't reach the surface. It is way below the surface. So I need to add more energy for my fluid to reach surface. As we can see here in the chart, I have a dead well which can't reach surface. Once I attach or add artificial lift type or even for example ESP, it will add more energy, so the gradient will be the same, but it will be moved to the right because I have added some energy here. So I draw the gradient, it will be intersect with x-axis, which is pressure at surface with a flowing wellhead pressure. I have here a drawdown because the ESP will cause a drawdown, a decrease in the bottom hole flowing pressure. So the flow will move from the reservoir to the bottom hole. Then the pump will increase the pressure. Here, as we can see, then the gradient will make the fluid reach the surface. So it was just a quick introduction to understand the difference between IBAR and VLP, which is describing the system. How can we do this analysis? We can do this analysis by many softwares like PipeSim and Prosper. We will do some examples in the main course using nodal analysis by PyPSIM and by Prosper. But just for to have a look on what will we do. For example, we have a well here. This will have an oil zone and in the upper and gas zone in the bottom. We have here all the data that is required for the modeling. We have the permeability for the oil zone, the reservoir pressure, the porosity, gas oil ratio, and so on, and the same for gas reservoir. In the next slide, we can see the detailed data for the well. We have the casing that is inside the well and the tubing also, and we have the deviation survey because all these data will be needed for the model to start the nodal analysis. I will share with you here a sample of what will we do using a pipe sim. This is the interface of the pipe sim. We will construct together the wellbore schematic with the casing and the tubing from these bottoms here, the tubular, where we insert the division survey and downhole equipment, the heat transfer coefficient, and the completion. We will insert the oil zone and gas zone and perform analysis from the upper here using the nodal analysis to check if this well will flow naturally or not from the gas or from the oil zone, and we will insert also the gas zone, and we'll see the impact once we produce both the oil and gas together. It will be in the main course, inshallah. This is sample also of the nodal analysis using the pipe sim. Once we run the system, there will be intersection between the IPR, which is highlighted here by the blue line, and the VLB, which is red line, and this well can produce naturally. We can do also some sensitivities on the reservoir pressure, decreasing the reservoir pressure, and seeing the impact on the well production. Same will be done by Prosper. This is the interface of the Prosper. We will do example with the Prosper, but not now. Then we will move to some quick comparison between the different artificial lift type. We have the root pump or sucker root pump. We have hydraulic pump or jet pump. We have semi-submersible pump, which is ESP. We have gas lift, plunger lift, and the progressive cavity pump. This is different way to bring well on production that is not capable to flow naturally because there is a depletion or to decrease in reservoir pressure make it hard to produce naturally. We have in this chart some comparison between the percent of the artificial lift. We can see here that the sucker root is a major method that used for production, and the ESP is the second one. Then the gas lift and jet pump will be minor. There is here some comparison, as we can see here, between the different artificial lift. When we need gas lift, when we need ESP, PCB, root pump, and jet pump. If we speaking about the mechanism in the gas lift, it is injecting high gas inside the bottom hole that will make the fluid lighter and move to surface. The ESP is a centrifugal pump that add energy to the fluid to reach pump. It is using a pump and motor and cable to transfer the electricity from the surface to the downhole. The PCB is a positive displacement pump containing from rotor and stator, driven by rod steering from surface to the downhole. For the root pump or the sucker root pump, it is also positive displacement pump or reciprocating pump, driven by a rod steering, and jet pump, which is hydraulic pump using a fluid that is injecting from the surface inside the tubing or anus based on the design and receiving back the production. And here it is comparison between the production rate. We can found that gas lift can produce up to 50,000, ESP can produce up to 80,000, but the PCB and the sucker root can have some limitation in the production rate. For the depths, there is some depth limitation in the PCB and also in the root pump. For the casing size, I think there's no limitation for anyone except for the ECB. If I have some liner or small liners that I can't utilize ECB. For the inclination or for the wheel geometry, I will have some limitation for the BCB and sucker rod because these two ways are driven by rod string from service to the downhole pump. So during the rotation movement of BCB or the up and down movement of the rod pump, there will be contact between the tubing and the rod. If I have some inclination, it may decrease the run life of the wheel. We will go in deep details for each artificial lift type, and we will mention the advantage and disadvantage of each one. If we speaking about the ESP, as we can see here, the system component are some component on the surface, which is the VSD or the drive that operates the well, the power source, and the transformer that step up the volt from low value to high value. Then we have our well, we have some tubing, and we have the ESP string in the bottom of the tubing. Starting from bottom up, we have sensor, motor, seal or protector, gas separator, and we have the pump. We will go in deep details for each one in the main course, inshallah. This slide also showing the main component of the downhole pump or the downhole string. For the sucker rod pump, it is the same also. It is have two main major components. We have the surface equipment and downhole equipment. Surface equipment of the sucker rod, it is a mechanical device that is converting the high-speed rotational movement from the prime mover to up and down movement that will be transferred to the downhole using the polished rod and rod string inside the tubing until it delivered to the downhole pump, which is working by a ball and seat mechanism that add more energy to fluid to move to surface. Moving here to the PCB pump, it is working also with service equipment, which is drive head driven by a motor and downhole pump. But in this case, or the PCB case, the downhole pump is consisting from two main major components, rotor and stator. The rotor is the moving part, which is helical shape that is rotating inside the stator, which give more energy to fluid to reach surface. The last one, or the gas lift here, we inject high pressure gas inside the annulus here. We inject the gas here. This gas will go inside the annulus or the backside, then enter the tubing from the deep point, making the fluid inside the tubing lighter and moving up till surface. We can have we have here some set of gas lift wells. We inject gas in the annulus, receive again from the tubing with production, then moving to the manifold, then to separator, separate gas, and back again to our system, and oil is go inside the pump to the storage tank and the produced water to the disposal well. For the last method of artificial lift, it will be the jet pump. We here in some cases inject a high pressure fluid inside the tubing. Then will be have a pump here that will have a nozzle and throttling valve that converting the high pressure and high speed fluid to kinetic energy that makes some drawdown inside the pump. This drawdown will suck fluid from the formation, and I will receive the production through the annulus. The jet pump can be used in higher depths, but the efficiency is not high. So we have discussed now different type of artificial lift: ESP, sucker rod, BCB, gas lift, and jet pump. Each one have advantage and disadvantage, and the application depending on your well condition and depending on the facility. If you have a source of gas, you can use a gas lift. If you have a power source, you can use ESP or sucker rod. The last slide here, we have the factors that affecting the artificial lift selection depending on well productivity. Do you expect high rate or low rate? the well depth, well geometry, the location if it is onshore or offshore, the fluid property, and if you have a rig or not, if you have a power supply or not, and also the economic factor and the personal experience inside your well. So, to recap what we have discussed today in this webinar, we have discussed the concept of the nodal analysis, IBR, VLB, how to understand them, and how to differentiate between the well that is flowing naturally and the well that need artificial lift. We discussed also the well types, and we discussed the artificial lift type. It was just a quick summary for the summary of introduction for the main course. I hope it is useful for you, and hope to meet you inshallah in the final course. So that is all from my side. Thank you for listening. I hope I can add some information to you. Thanks.